Hello, everybody, and welcome to the Georgia Tech Graph Theory seminar. Our speaker today is Ruth Luo from University of California, San Diego, and she will tell us about forbidden traces in hypergraphs.
Okay, thank you. Thanks, Anton, for inviting me, and thank you, everyone, for coming. So this is joint work, two different projects, one with Zoltán Füredi and one with Sam Spiro, who is a graduate student at UC San Diego. All right, so here's some motivation. If we have two matrices, M1 and M2, we say that M2 is configuration of M1. If there's some submatrix of M1 that is a row or column permutation of M2. So we contain it essentially as a submatrix. And if we have a simple matrix, which means a 0, 1 matrix, with n rows, such that every column of n has exactly R1s, so we can view this as each column is like the incidence vector of a hyperedge, and we're looking at an R uniform hypergraph. Okay, so what we're going to talk about today is what it means if we have some configuration, which is an incidence matrix, this case of a graph. So for instance, here I have the incidence matrix of C4. And if I look at the corresponding hypergraph, what that means is I have some 4 vertices, V1, V2, V3, V4. And if I look at, for instance, the first column, it contains the first 2 vertices and some other, say, R-2 vertices, where these R-2 vertices don't represent or don't intersect with these representative vertices. Okay, similarly, the second edge contains V2 and V3, and then maybe some part of it intersects over here, but we don't care, and so on. Oh, okay. And so essentially what's going on is we have some subset of vertices, V prime, and some subset of edges, E prime, such that if we look at the hypergraph, which is sort of induced by these, so what we do is we restrict to only those vertices, and only we intersect the edges with those vertices, then we're going to get something which is isomorphic to the graph F. And that is going to be called a trace of F. Okay, so in other words, we have this hypergraph H, we have some graph F. H is a trace of it if we can look at some subset of vertices A, look at this induced hypergraph, and we get something isomorphic to F.
Can I ask a quick question about this?
Yes.
Just to clarify, when we look at this set, E intersect A, E an edge of H, do we count these with multiplicity or no? So if there are several edges that overlap with my set A in the same 2 vertices, is it bad for me?
We also restrict to, I see what you mean. No, that's fine.
Okay.
So there could be some extra edges that we don't care about. So this is just what it means to be a trace of F, and then containing the trace of F means we have some.
Okay, I see.
Okay, so here's another definition. H is a trace of F if we have some bijection from the edges of the graph to the edges of the hypergraph, such that for every edge xy in the graph, I look at the edge that it gets mapped to, the hyperedge, and if I take the intersection with the vertex set of F, then I get exactly those 2 vertices and no other ones. Okay, so in the matrix problem, this was called the forbidden, or the configurations. For hypergraphs, this is called trace, and then it's also sometimes called induced parish, but we'll use trace. And here's some examples. So these are 3 uniform hypergraphs, and these vertices here that I'm circling, these are going to be called our representative vertices. And in the first 2 examples, we have 2 different examples of traces of C4. And this third example over here, this is not a trace of C4, because for instance, if I look at edge 2, it contains 3 of these representative vertices. Okay, so hopefully then the definition is clear. All right, so let's talk about extremal functions. So for a graph F, we have this Turon function, this x and f, which is the maximum number of edges in an n-vertex F-free graph, which means we don't contain F as a subgraph. So now we want to define something similar for hypergraphs. Okay, so first let's let this trace of f denote the family of hypergraphs that are traces of f's, for which there are multiple different hypergraphs which can be a trace of f. And now we have this analogous definition for hypergraphs, where we put this subscript r to denote the uniformity of the hypergraphs. So this function is the maximum number of edges in an n-vertex R-uniform F-free hypergraph, where F is some family. And not surprisingly, we're going to look at what happens when we forbid these traces of F. And in some cases, our results, we're only going to look at the order of growth of this. As R grows, the uniformity grows, and then we assume that n is very large in order for our asymptotics to make sense. Okay, so here are some past results. So actually there's only one exact value of this Turan of trace of F, and that's the case where F is equal to the triangle. So we forbid the triangle trace, and this was proved by Mike Piccolelli in his PhD thesis. So he showed that for all R, he got this bound, which is roughly n squared over 4. And perhaps this looks a little bit suggestive. So the construction is, we're going to start with a complete balanced bipartite graph. And as we know, this is the maximal graph, which forbids just a triangle. And to make it into a hypergraph, what we're going to do is add r minus 2 new vertices, and then just extend every edge to include these new vertices. So we go from 2 uniform to r uniform. This is the number of edges we have. And to see that it is triangle trace free, so if it did have a trace of a triangle, one of the representative vertices must be contained in one of these r minus 2 new vertices. But those vertices are contained in every hyperedge of our construction. And there's no vertex in the triangle which is contained in every edge. So that's the reason why it doesn't have a trace of a triangle. All right, and then Mubai and Jal also proved some similar results. So asymptotically, they determine the order of this Turan number of the trace of K4 for all R. So their construction was similar. We just start with like a 3 uniform Turan hypergraph, and then just add new vertices, include them in the old edges. And they also proved it for general cliques, so cliques of size T, but only for the case where the uniformity is around the size of the clique. So either T or T plus 1. Okay, and this is their analogous result. So almost everything else is open. And I want to talk about these constructions. So before, what we had was we started with this complete bipartite graph. We added some new vertices and got a new construction that way. So something similar works for any graph F, which is not just equal to a star. So what this says is, let me take a construction of an R minus 1 uniform hypergraph, which has no trace of F. And sorry, this is old notation, but this should be trace of F. So what I want to do is construct a new example. Again, I add this new vertex. I include it into every existing edge. And so now I go from R minus 1 uniform to R uniform, and I also have one more vertex. And we claim that this also doesn't have a trace of F. So if it did, this new vertex should be a representative vertex. And then that vertex is now contained in every single hyperedge. But the only graph which satisfies that there's a vertex contained in every single edge is exactly this star. Okay, so in the special case, or I guess the general case, what we have now is a lower bound for this Turan number in terms of the Turan number of R minus 1 uniform. So this function as a function of R should be non-decreasing if we only care about the order of growth. Okay. feel free to ask any questions. So I don't have like chat or any of the cameras open, so you can stop me whenever you want. Okay, so what we want to do is try to compare this to some extremal type of problems in graphs. So one way you can do it, if we have an R uniform hypergraph, we can define what's called the two shadow of the graph, or the hypergraph. So this is a graph on the same vertex set where we put an edge xy for every pair xy, which is contained together in a hyperedge of H. So if we started with something that was R uniform, a hypergraph, then what that means is every edge, which has size R in the hypergraph, is going to give me a clique of order R as well in the shadow. Okay, and this implies that the number of edges of our hypergraph is at most the number of cliques of size R in its shadow. And we get the nice property that if our hypergraph originally did not contain a trace of F, that means, if our hypergraph originally contained a trace of F, that means our shadow is going to contain a copy of the graph F. But the converse is not always true. So for instance, here I have a hypergraph and here I took its shadow. In the shadow, I have some very long cycles, but in the hypergraph itself, the longest trace of a cycle I have is length 4. Okay, so unfortunately, we don't have this like sort of one-to-one correspondence, but let's see what we do get. So if we denote this function by x and krf, so this is called the generalized Turan number. And what we're doing is this function is counting the maximum number of cliques of order R in an F-free graph. And in the case where R is equal to 2, this is exactly just the Turan number. So this is a function which we talk about for graphs. And so how does it relate to this hypergraph Turan number? Okay, so what we get here is that this hypergraph R uniform Turan number of the trace of F is at least this generalized Turan number. And the way to see this is, so let's take a construction of a graph which maximizes the number of R cliques while being F-free. And then we construct a hypergraph by taking every clique of order R and turning it into a hyperedge. And if our graph was F-free, then the resulting hypergraph will be trace of F-free. All right, so previously what we saw was this non-decreasing growth of this function. And now we can use as another lower bound this generalized Turan number inside graphs. Okay, and so as a corollary, we get that this Turan number of the trace of F is at least the order of the maximum number of cliques of order S in an F-free graph. But here, the size of the cliques can be any size, any number from 2 to R. So we will be bigger than all of those functions, or at least as big as all of those functions.
Do we think of R as a constant here?
Well, you should think of it as n is very large and R is growing, and we're tracking the order of this function as R grows.
Okay.
Yeah, but you should still think of R as like, you know, not
much
like
less than n.
Yeah, exactly. Okay, any other questions? All right, then I'll move on. So this corollary is just what I wrote before, that the order is at least the maximum of all of these functions. And in 2017, Shawley and Spiro, so what they did was they proved a matching upper bound, at least in terms of the order of growth. And they determined it for the case where F was equal to this complete bipartite graph, KAB, which also they had some restrictions on A and B and also R. Okay, and then this bound here, this explicit bound, was due to Alan and Schickelmann. So in 2019, Zoltán, Füredi, and we generalized their proof, and we showed that not only do we get a matching upper bound for this KAB, but we can do it for any graph F, which is not just the star, and we get this bound here. Okay, so just a couple comments. So it's still in terms of this generalized Heron function, which in general, there are some results, but mostly a lot of things are still open. So we kind of get it in terms of this other nebulous extremal function, but at least this one is a little bit more well-studied than this trace of F problem. And we also did get results for stars. I just didn't include them here because it wasn't as important. Okay, so that was our theorem, and I will briefly go through a proof idea. So the proof idea is that we want to restrict to a smaller subhypergraph of our hypergraph, which has very large minimum degree. But what we mean by minimum degree here is minimum codegree. So if we have some natural number alpha, we say some subhypergraph A of H is an alpha core if for every subset of size r minus 1, so every r minus 1 vertices, either those vertices are not contained in any edges together, which means they have codegree 0, or they're contained in at least alpha edges together. Right, so this d sub alpha, this is denoting the codegree, which means the number of edges that those vertices are contained in together. All right, so here's a lemma. So if we do have a alpha core, where alpha is sufficiently large compared to the number of vertices, then if the 2 shadow of this alpha core, which is a graph, if that contains a copy of F, then A will also contain a trace of F. And okay, let me draw the proof here. So suppose in my shadow, I have some copy of F. Okay, so here's F. And what I want to do is map these to hyperedges in A. And I'm going to do it in such a way that, so for every pair of vertices, which are an edge in here, I pick a hyperedge in A, which contains those 2 vertices, but has a minimal intersection with the other vertices. And so if I can choose them in such a way that each of these hyperedges contain only those 2 vertices that I want, that's going to give me a trace of F. So then the problem is if I have some edge, so okay, so the graph edge will be xy, it gets mapped to some edge, say f of xy, whoops, f of xy. But this f of xy contains some other vertex z here. And now we're going to use the property of the alpha core. So the alpha core says if I pick some r minus 1 vertices, which I'll pick everything except for z, then they have very high codegree. In particular, I can pick some edge here, where the last vertex, which is going to be replacing this z, let me call it z prime, lives outside of these vertices. And I just keep optimizing this way until I get a trace of F. Okay, so the rest of the proof was basically to show that the alpha core does exist and that we can control like the amount of edges that we delete to get to the alpha core. So I won't show those details, but what I'll show is a special case. So for example, when our graph is equal to a cycle, so CL for some length L, and suppose we have some hypergraph, which is R uniform, no trace of CL. What we want to show is that the L core of this hypergraph is empty. And so the way we do that, if we have at least one edge in the alpha core, or sorry, the L core, then when we look at this edge, its shadow contains a KR. And in particular, the KR contains a copy of the cycles CT for any t less than or equal to R. And for any of those, we can extend them to a trace of the CT in the original hypergraph. Okay, so now we consider the case where this L, which is like the forbidden length, is strictly bigger than R because we handled all the smaller cases already. And so what we claim now is that if I have some trace of CT in my core, then I can extend it also to a trace of CT plus 1. And I can keep doing this until I get something of size L. And so the way we do that, so suppose I have in the trace of the cycle, something like this, I have these vertices x, y. What I'm going to do is pick another vertex, z, inside this f of x, y. And then for one of my R-1 sets, I take every vertex in this edge except for Y. And then I find now this new edge using the properties of the core, which replaces Y with something outside of these representative vertices. And then I do the same thing for X instead. So now what I get is by replacing this edge and using instead these two edges, I can extend the length of the cycle by 1. And I keep doing this until I get something of the forbidden length that I want. Okay, so we had some corollaries from this. So in particular, we had this Turon number of the trace of CL, which was only in terms of the Turon number for graphs. So now we don't have like this generalized, like the maximum number of cliques here anymore. Okay, so we get this bound here. And also as a corollary, this will tell us what an upper bound at least for this maximum number of cliques of order R in a CL-free graph. So this result was already known by Guri and Lumens, but this gives us a different proof of the same result. Okay, so that was for cycles. And what we wanted to do was try to get some better bounds for some specific graphs F. And so the first one that we looked at with Sam Spiro was the case where we forbid traces of C4. And then we had some early version of the proof that we saw could actually extend to forbidding K2Ts. So I want to go through that. So here's just some history of the results of forbidding these K2Ts. The first two results are for graphs. All right, so this is just like the Turon number of K2T. And this third result, so by Alon and Shikomen and also Gerbner, Mafuku, and Wieser. So they proved some other results, but it gave us a lower bound for this 3 uniform, no trace of K2T. All right, so in particular, they have something of the order 1/6 T to the 3/2 and to the 3/2. So that was their lower bound. And so with Sam Spiro, we proved an almost matching upper bound. And in particular, this works when T is at least 14. So what we showed was that this Turon number of the K2T trace in 3 uniform hypergraphs. So we still get this 1/6 T to the 3/2 and to the 3/2, but we also get this smaller order term here, which perhaps someone could try to remove in the future. Right, so in particular, if we care about only N and T very large, then we are tending towards the correct ratio, this 1/6. All right, so here's the proof outline. So I pick my hypergraph H, which is 3 uniform and contains no K2T trace. What I want to do is partition the edges and handle them separately. So the first set I look at will be, I call it here A. These are the hyperedges in H, so each hyperedge is 3 vertices. At least one pair of these vertices has codegree 1, which means that pair of vertices is only contained in that edge. And then H minus A will be everything else, which we will handle later. Okay, so the first part will be an easy upper bound for the size of A. So we claim that the number of edges in A is at most just the Turon number of K2T. And how do we do that? So we have these hyperedges in A, and for each one of them, I have a pair with codegree 1. I'm going to take one of those pairs for each hyperedge and then create a new graph using those edges, those pairs. So this is called our G sub A, and it's easy to see that the number of hyperedges in A is the same as the number of edges in GA. And now what we're going to do is show that GA cannot contain a copy of K2T, which will give us this upper bound here. Right, so if we had some copy of K2T here, let's look at a pair of vertices, so X, Y, this edge here. And let's call the hyperedge that it gets mapped to just F1 for now. So is it possible that F1 contains another vertex in this set here? Well, if it contained, for instance, the Z, okay, so here's X, here's Y, then this pair, ZY, well, it was also mapped to by another edge, which was different from F1. So maybe something like this, F2. But now we have that this pair YZ has codegree at least 2 in our hypergraph, giving us a contradiction. Okay, so we get this found here. All right. So the rest was a little bit more complicated to handle. So we look at the set of edges, which was not in A. And the set of edges, there's at least, sorry, all the pairs have codegree at least 2. So 2 definitions, just working in regular graphs. So probably everyone knows dominating sets. A dominating set is a set of vertices such that every vertex is either in the set or has a neighbor in that set. And we say that this neighbor dominates the vertex. What we want to define is something called dominated sets. So this is still in graphs, but now we allow some loops in the vertices. So a dominated set is a set T such that every vertex inside this dominated set either has a neighbor outside of it, so it's dominated by something outside, or has a loop, in which case we say it dominates itself. So this is kind of like the opposite of a dominating set. And also 2 more definitions, or just 1 more, I guess. So if I have a pair of vertices, X, Y, in my hypergraph, I'm going to define the set N to be the subset of vertices such that X, Y, and say this vertex U are contained in an edge in this H minus A. And then I define 2 graphs, the link graph of X and the link graph of Y on the set N. Okay, so for our version of the link graph, the vertex set is exactly these vertices here. And we put an edge between 2 vertices in N. If, so for the link graph of X, so I put an edge between U and V if X, U, V is a hyperedge in H. And then moreover, every time there's some vertex Z, which is outside of N, such that X, U, and Z form an edge in H, then I'm going to put a loop on U, a loop edge. All right, and by the definition of this H minus A being the set of edges in which everything has codegree at least 2, the link graph will have no isolated vertices. Okay, and then we define the link graph of Y similarly. And here's our claim. So if we have a set T, which is at least size little t, which is dominated in both the link graph of X and the link graph of Y, then we claim that our original hypergraph must contain a trace of K2T. And okay, so let's see what's going on here. I have my vertices X and Y, and I have this dominated set T. So I pick a vertex in this dominated set. And in the link graph of X, it's dominated by some vertex that lives outside of T. So in particular, we have this edge L, which includes U and X, and then some vertex outside of T. We do this for every vertex here, and then for every X and Y pair. And that's going to give us a trace of K2T. Okay, so that's the point of the dominated sets. They help us find these traces, because the only thing we're trying to avoid is if we have an edge which intersects like multiple vertices in this set T. Okay, so now what we want to do is show the existence of large dominated sets in both L of X and L of Y. All right, so here's a lemma we had. If these link graphs have no isolated vertices, then there exists a set D, which is dominated in both L of X and L of Y, of size at least the number of vertices over 3. And well, what was the number of vertices in this link graph? It was just defined as the vertices U such that X, Y, and U form a hyperedge. In other words, this is just the co-degree of x and y in this h minus a. Okay, and then what this lemma says is that then this co-degree can be at most 3t. Otherwise, we will find a dominated set of size at least t, which gives us a bad trace. All right, so actually the case is nicer if we also have some bound on the minimum degree. So I don't know who originally proved it, but there's like this proof in the Alon and Spencer, this probabilistic method book, where you do this random construction of a small dominating set in any graph. So the same proof shows that if we have delta at least 2, then we have a dominated set in our graph of size at least this 1 minus epsilon, where epsilon is now this function of delta. So roughly 1 plus log of delta over delta. Okay, so we can find very large dominated sets. And so what this shows is if both the link graphs have very large minimum degree, we can find large dominated sets in each of them, and then in the intersection, we have a set which is dominated by both. And so in this case, what we show is that the number of vertices cannot be too large in the link graphs, which is the co-degree. And it's roughly something like 1 plus 4 epsilon times t. Okay. So now what we want to do is further partition these remaining edges into 2 sets, basically the ones with sort of medium co-degree and then large co-degree. So the set B will be the edges where at least one pair has small co-degree, so at most delta, in H. And then the set C will be the edges in which every pair has co-degree greater than delta. And so let's see how we handle B. So for every hyperedge in B, we select a pair with small co-degree, and we construct a graph using those. So in this graph, each edge is mapped to at most delta times, and we claim that it does not contain a K6T, right? So if it contained a K6T, which I just used the same picture as before, well, we know that the co-degree of x and y, we showed that was at most 3t. So maybe, whoops, sorry. I might have some edges that look like this, but there's not that many vertices that satisfy that. So let's throw those vertices out, and we still have at least 3t vertices here. And now we can show using the lemma that we had before on the link graph of x and y that we will have a dominated set of size t, which gives us a bad trace. Okay, so here then the number of edges in B is bounded by delta times the Tron number of K26T. Sorry, this is supposed to be a complete bipartite graph, not the complete graph. Okay, and then finally, we can talk about how to handle C. This is the set of edges in which every pair has co-degree at least delta, which implies that the link graph has large minimum degree. And now we want to use this sort of probabilistic method to show that there are large dominated sets. Okay, so here's some facts. We show that, okay, so by the thing I just said, by lemma 2, there exists large dominated sets of size at least, so roughly this 1 minus epsilon times the number of vertices in the link graph. And in particular, if our delta is at least 14, we can choose dominated sets and take the intersections such that the intersection of those dominated sets still has size at least t. Okay, and that's if the number of vertices in the link graph is very large. So what this tells us about the subhypergraph H is the following, or sorry, C is the following. So first of all, C is still K2T trace free because it's just a subhypergraph of the original thing. And from this condition for the dominated sets, we have that every co-degree is at most this 1 plus 4 epsilon t inside of C. Okay, so we call this value K. And moreover, by the definition of C, every codegree is at least delta. So we have this like lower bound and upper bound on the codegrees, but we look at the codegrees within the different hypergraphs. Okay, so let's see just the general proof for the rest, the general idea for the rest of the proof. So I take some vertex X, just any vertex, and I look at the edges containing it. And the set of vertices here, I'm going to call like this first neighborhood of X, but only looking at the edges in C. Okay, so let me take some vertex Y, which is in the first neighborhood of X. And I want to show that there are not too many edges of the form Y, some other vertex in this first neighborhood, and then maybe something else outside here. So basically the number of edges which intersect this neighborhood in at least two vertices. Okay, so first of all, I'll show that if we have too many edges which intersect multiple times in this neighborhood, then what I can do is, so I redrew this here, I can again just take this linked graph of X and Y, and in that I will be able to find a trace of K2T. Okay, so we don't have too many edges that look like this. So the remaining edges have to look like this. They have at least, or they have two vertices that leave this neighborhood. And potentially I can have many edges like this. But now if I consider another vertex here, Z, which is in the first neighborhood of X, I want to show that now if I look at its edges that go outside, then they cannot overlap in too many vertices. Because again, then what I'm going to do is now take the link graph of Y and Z, and then I can use my dominated set lemmas to find a large trace there. Okay, so in other words, what we showed is that these vertices in the first neighborhoods cannot have too large degree. They cannot have too many edges because we can control them in both steps. And in particular, we can show an upper bound for the average degree of each vertex in C, which is given by this, so roughly 1/2 k to the 3/2, which is this value here. And so using this average degree, now we can get an estimate for the number of edges, of course, or not an estimate, an actual result. So putting together everything we had these three different classes of edges, and these are the bounds that we got. And then in the end, we just need to optimize delta, and that's going to give us the result that we wanted in the end. Oh, sorry, this should have a n to the 3/2. All right. Okay, so let's see a couple open problems. So first of all, this is related to another sort of famous hypergraph-Turon problem, which is called the Berish-Turon problem. So for a graph F and a hypergraph H, we say that H is a Berish F if there exists some mapping, we call it phi, from the edges of the graph to the edges of the hypergraph, such that for every xy, which is an edge of the graph, the vertices x and y are contained into whatever hyperedge we map it to. And in particular, our trace of F, this is a special class within the Berish Fs. And what this tells us is that, sorry, again, this should have R here, this should have R here. The Turon number of Berish F is at most the Turon number of trace of F. Okay, so what we wanted to do was also look at how these functions compare. So here I drew a diagram. So for each of these functions, for instance, for this Berish of F, forbidding it, we will say that the maximum number of hyperedges we can have is some constant times n to the alpha. And what we want to look at is how alpha grows as the uniformity is growing. So in all of these cases, here we have Turon number for the trace of F, and also this generalized Turon number, which is maximum number of cliques in an F-free graph. So in all of these cases,
sorry, Ruth, do we actually know that they're of this form? That there is some, say, some alpha such that the extremal number of Berge F is asymptotically constant times n to the alpha for, say, fixed R?
Are you saying if the limits exist, basically?
Yeah.
Yeah, we do. I think
Okay.
it's basically the same sort of argument that you can use to show like that the regular Turon number has a limit.
Okay, I see. Thank you.
Yeah. Okay. So all of these sort of have the same behavior in the case where the uniformity is at most this chromatic number -1. So basically for the hypergraphs, the examples we take will just be like a hypergraph Turon construction, this balanced complete R-par type thing. Okay, and then there's a result due to Masuku and Tompkins and someone else, I forget, sorry, which says that for Barish of F, there exists some R naught such that for every R, which is at least this R naught, this will be a threshold on the uniformity. Then if we forbid this Barish of F, eventually the order of growth of this is actually going to shrink below n squared. So it's even smaller than the Turon number in a graph. Okay, so otherwise we don't really know what's going on here. We don't even know if it's decreasing, increasing, or whatever, but eventually it goes below n squared. And actually this is sort of misleading too. Okay, and then because we don't really know the growth here. Okay, and what we showed was for the trace of F, we showed that the Turon number for trace of F is at least the maximum order of maximum number of cliques. And in particular, it's going to stabilize at some point and then just stay the same. Okay, so in this sense, it's sort of nicely behaved compared to this forbidding Barish F problem. Right, and so there's still pretty much everything in this range is open, even for non-bipartite graphs. Let's look at a couple more open problems. All right, again, I said earlier that the only known exact case for this forbidding trace of F was for the case where we forbid the trace of a triangle. So everything else is open. You can try to attack that, or you can try to attack this conjecture by Mubayi and Jal for forbidding trace of KT, but now for any R. Okay, so is this the correct order? And also in the same paper that I presented today, so we had this result for forbidding trace of C4. So the lower bound is just given by the Turon number of C4 in graphs. And the upper bound, we have this 5/6 into the 3/2. So we do believe that the answer should be closer to the lower bound, or at least I do. Don't want to speak for him. So this is still open. We're really not sure how to do it. And then also this was for 3 uniform, but it'll get harder and harder for 4 uniform, 5 uniform, and so on. So you could also try to work on that. And then I also wanted to talk about one other extremal problems. So there was like this Barish F and then this trace F, and on the other extreme, we have this expansions of F. So if I have a graph F here, the expansion of F is the hypergraph, which is R uniform, where basically for each edge here, I just add R-2 new vertices in a way that these new vertices are not overlapping in any way. Okay, and so there are many open Turon type problems for forbidding these expansions of graphs. And I'll end it there. Thank you.
Thank you, Ruth. Let us all thank the speaker. Are there any questions? Do we know when this quantity, what was it, beta of R when it stabilizes? For which value of R? Do we have some estimates for from which point on it becomes the same?
So for most cases, no. Actually, I don't know of even one case where we do know. So it's basically like it relies on this maximum number of cliques problem. And so for maximum number of cliques, if I have I'm forbidding some graph F. And if I know that this uniformity is bigger than the number of vertices in F, well, then my graph cannot contain any KRs because then it will contain a copy of F, right? So this will equal 0. And then similarly, we know like what happens when we're before the chromatic number. But here, this is really unknown for this generalized Ron function.
I see. So we somehow abstractly know that it has to stabilize somewhere, but we have no.
Yeah, or this will maximize somewhere,
right.
And wherever it maximizes, the other function will stabilize.
Yeah. I see. Are there any other questions? Okay, if there are no more questions, then let us thank Ruth again. And I have an important announcement about next week's talk. So the speaker will be Louis Esperet from Grenoble, and due to the time differences between the speaker's time zone and our time zone, the time of the seminar will be different. We'll start at 12:30 rather than at 3:45. So the seminar next week, 12:30 p.m.